Welcome to this explainer. Today, we're diving headfirst into the incredible microscopic world of chemistry. And hey, if you're a complete beginner to the subject, you are in exactly the right place. We're going to break down the basic rules of how our physical universe actually operates. So let's mentally throw on our lab coats and zoom way in to discover what makes up literally everything around us.
Okay, picture this. You've got a crisp red apple sitting right in front of you on a cutting board. You take a knife and you slice it perfectly in half. Then you take one of those halves and cut it in half again, and again, and again. Now imagine you had a magically sharp knife and could just keep cutting that apple into smaller and smaller pieces forever. What would you eventually get? Would you just end up with an infinitesimally tiny piece of apple, or would you eventually hit a wall? Is there a literal stopping point where it just can't be divided anymore? Keep that mystery in the back of your mind, because that exact question is what kicked off the entire science of chemistry.
Here's a quick roadmap of what we're covering today. First, the ultimate building blocks. Second, the history of the atom. Third, how small are atoms. Fourth, the rules of matter. And finally, proving the law. Section 1. The ultimate building blocks. What is everything made of?
So, going back to our apple thought experiment, the answer is yes, you absolutely hit a wall. If you keep dividing matter, you eventually arrive at a fundamental base unit, and we call these units atoms. Atoms are the literal building blocks of all matter. You can kind of think of them as the invisible Lego bricks of reality. Everything you see, everything you touch, even the air you breathe is made of these tiny bricks stacked together in different complex ways. In modern chemistry, an atom is defined as the absolute smallest particle of an element that can actually take part in a chemical reaction. They are the true foundational basis of our physical world.
Section 2. History of the atom. The early detectives. You know, long before we had incredibly powerful microscopes or high-tech laboratories, ancient philosophers were already puzzling over that exact same apple experiment. Way back around 500 BC, an Indian philosopher named Maharishi Kanad came up with a genuinely groundbreaking theory. He argued that if we go on dividing matter, which he called padarth, we would inevitably reach the smallest possible particle, beyond which further division simply can't happen. He named this indivisible particle Parmanu. And what's wild is, around that exact same time, the ancient Greek philosophers Democritus and Leucippus were having the exact same realization. They called these indivisible particles atoms. So you have two entirely different cultures, separated by thousands of miles, independently discovering the exact same fundamental concept of the universe, over 2.5 millennia ago. Section 3. How small are atoms? Visualizing the invisible. So we know what they are, but just how tiny are we talking? Well, they're so impossibly small they can't even be seen with standard, highly powerful microscopes. To really wrap our heads around this, let's walk down a scale of relative sizes. We start at the top with our everyday apple, which has a radius of roughly 10 to the power of -1 meters. Shrink down to a little ant, and we're at 10 to the -3. A single tiny grain of sand is 10 to the -4. Now we're getting super microscopic. A molecule of hemoglobin floating in your blood is 10 to the -8. A molecule of water is 10 to the -9. And finally, sitting at the very bottom, we have a single atom of hydrogen at a mind-boggling 10 to the power of -10 meters. That is almost incomprehensibly small. Because they are so tiny, scientists actually need a special unit just to measure them. Atomic radius is measured in nanometers. And let me break that math down real quick. 1 divided by 10 to the power of 9 meters equals 1 nanometer. Or, to put it much more simply, one single whole meter contains exactly 1 billion nanometers. So when we're measuring atoms, we're talking about things that are just fractions of a single billionth of a meter. Section 4. The rules of matter. Lavoisier's laws. All right, meet Antoine Lavoisier. This guy, along with Joseph L. Proust, is basically a legend because he essentially laid the entire foundation for modern chemical sciences. How did he do it? By establishing the laws of chemical combination. You see, before Lavoisier, chemistry was honestly a bit messy. It was almost treated like magic. But Lavoisier, he brought strict, reliable rules to the table. He figured out the basic laws that tell those tiny atomic Lego bricks exactly how they're allowed to combine and interact with each other in the real world. And the most famous of these rules, the absolute golden rule you need to memorize as a beginner student, is the law of conservation of mass. It states that during a chemical reaction, mass can neither be created nor destroyed. This means the universe absolutely does not do magic tricks. You can't just make atoms pop into existence out of thin air, and you definitely can't make them vanish into nothingness. They simply rearrange themselves into new patterns. We can actually simplify this big concept into a very straightforward, non-intimidating equation. The total mass of reactants will always equal the total mass of products. Now, reactants is really just the fancy science word for the stuff you start with, and products is just the stuff you end up with after the reaction happens. The mass, the physical weight, has to balance perfectly on both sides of the equation, every single time. Section 5, Proving the Law, Activity 3.1. Let's look at this real-world example with mercuric oxide. Say we start with exactly 100 grams of a reactant, and we force a chemical reaction that breaks it apart. We don't just get random, unpredictable amounts of new stuff. It splits perfectly into exactly 93 grams of liquid mercury and exactly 7 grams of oxygen gas. 93 plus 7 equals 100. Spot on. The starting mass perfectly matches the final mass. Nothing was lost, nothing was created. Okay, let's pretend we are in a classroom lab right now. And let's prove this ourselves using a classic experiment called Activity 3.1. First, we take two different chemical sets. We'll just call them X and Y for now. X could be copper sulfate, Y could be sodium carbonate, doesn't really matter. Step 1, we carefully pour solution Y into a glass flask, and we put solution X into a much smaller glass ignition tube. Step 2, we put this whole setup on a scale and weigh it super carefully before anything mixes. Step 3, we tilt the flask so the smaller tube spills, mixing X and Y together to trigger our chemical reaction. And step 4, we reweigh the entire thing after the reaction is totally finished to check for any changes. Now, if you look at the setup, you can see the flask holding solution Y and that little ignition tube holding solution X suspended by a thread. But look right at the top. There is a cork tightly sealing the flask. Why is that little piece of cork absolutely crucial? Because if a gas is created during our chemical reaction, we cannot let it float away. If gas escapes into the room, our final weight is going to be lighter and the whole experiment is ruined. The cork ensures our little environment is totally locked down, so not a single atom can sneak in or out. So, drumroll please, after we tilt the flask, watch the chemicals vigorously mix and react, and then pop that sealed flask right back onto the scale, what happens? The mass remains completely constant. The final weight on the scale is the exact same number it was before the reaction even started. Boom! We have successfully proven the law of conservation of mass. The atoms inside definitely rearrange themselves to form brand new chemical products, but every single atom we started with is still trapped in that flask, accounting for every single gram of mass. So, we've just seen how this law works beautifully for chemical changes inside a closed flask. But I want to leave you with a bit of a challenge to test your new chemistry skills. Can you think of an example of this law of conservation of mass when it applies to a physical change instead of a chemical one? Think about everyday things like ice melting in a glass or a pot of water boiling away into steam on the stove. Does the total mass actually change in those situations? I'm going to leave you to ponder that one on your own. Keep questioning, keep exploring, and thanks for joining me today.